This video is on precipitation reactions, what it means to be a precipitate, and the idea of solubility, and then a quick discussion of all of those things into double replacement reactions. Okay, so we have talked about the word precipitate before, and so a precipitation reaction is, hold on, my pen's not on, is a reaction that produces a precipitate. I will tell you that precipitation reactions are double replacement reactions. So precipitation reactions kind of fall under the umbrella of double replacement. Not all double replacement reactions are precipitation reactions, though. Okay, so then what is the definition of a precipitate? That is something that we had learned previous to this lesson, and a precipitate is an insoluble solid that forms from mixing two aqueous substances. So I demoed a precipitate for you in class, and I did a couple. One of them, though, that's a fairly common precipitation reaction to look at, is where you have a solution. It's a clear solution in a test tube, so it looks just like water. And then you add a second clear solution in a test tube. So those are both aqueous substances. And when we mix those together, we got kind of a milky white substance, which if we let settle, given, enough time for it to settle, it sunk to the bottom, and then there was some liquid on top. And so this precipitate is the solid at the bottom of the test tube. So in that case, the precipitate was white, but we also saw a few demos where we had, I'm not sure, but maybe a blue or a pink or a green precipitate. Some precipitates are colored, some are white, and we'll get into that discussion a little bit later on. So that is the definition of a precipitate and a precipitation reaction. So from here, one thing we have to talk about is that precipitation reactions and even double replacement reactions are governed by something that we refer to as solubility rules. And so the word soluble means to dissolve in water, and the word insoluble means does not dissolve in water. So what we're looking at now is a discussion of how do we know if something, how do we know to expect if something would dissolve in water or would not dissolve in water? And so the way we're going to answer that is with something called solubility rules. There are lots of ways to present these rules, lots of different charts, and this is the chart that I use. And if you notice, we're going to talk about this chart for a couple minutes. It's broken into two separate sections. The top chart has the title soluble ionic compounds, and then the bottom chart has the title insoluble. Okay, so the top chart, soluble, the bottom chart, insoluble. And the way we're going to use this chart is to look at the anion in a particular compound. So if we see right here, these are all anions, the negatively charged species. So what we'll do is we'll look at a compound, we'll figure out who the anion is, and then we'll come to the chart to figure out if we would expect that compound to be soluble or if we would expect that compound to be insoluble. So before we get into the practice that I have on your paper, let me just make up a couple real quick. Let's do MgCl2 and Ag3. Is that one I gave you? No, PO4. Okay, so what about these two compounds? Like if we found them on a shelf, okay, in the solid form, would we expect them to dissolve in water or not dissolve? Well, at this point, you should say, I have no idea. How am I supposed to know? And so we're going to use this solubility rules to answer the question about these two compounds. So the first one, magnesium chloride, the anion is chlorine. So here's chlorine in the chart, right? Chlorine's in the upper chart, so mostly soluble. However, there are some exceptions. And the exceptions are if it's with silver, mercury, or lead, then it's an exception to being soluble. which would mean it's insoluble. Well, but magnesium's not an exception to this. So magnesium chloride we would expect to be soluble. Knowing that it's soluble, if we put it into water, it will dissolve, and we'll give it the abbreviation AQ for aqueous. Now, a second example is silver phosphate. So what about silver phosphate? So we look up phosphate in the chart. Phosphates are mostly insoluble, with a few exceptions though. NH4 plus and the alkali metal cations. That's your group 1s. Okay, so lithium, sodium, potassium. So knowing that silver is not a group 1 cation, we would expect silver phosphate to be insoluble. If something is insoluble when I put it in water, it will not dissolve, and so therefore it's going to stay in the solid form. So there's 5 practice questions. If it were up to me, I would tell you to pause the video, try using this chart on your own to decide if these are soluble or insoluble. But of course, if you don't want to do that, I will just go right into these. So the first one, sodium chloride. Well, if we think about it, just using our common sense, that's table salt, and we all know table salt is soluble. However, let's prove it to ourselves. So chlorine in the upper chart, mostly soluble, only not if it's with silver, mercury, or lead. Well, that's not the case here, and so we would expect sodium chloride to be soluble in water. Copper 2 hydroxide, not that I need to write the formula, but I will. So hydroxides are insoluble for the most part. Okay, insoluble, unless it's with NH4 or group 1 or calcium, strontium, or barium. Well, it's with copper, so that's not the case. So we would expect this to be insoluble. Magnesium carbonate. Carbonate is also an insoluble ion. Only exception is if it's with NH4 plus or group 1s. Be careful, magnesium is not a group 1, it's a group 2. Oops. So that means that this is in fact insoluble. If we put that in water, we would expect it to not dissolve. Okay, barium sulfate. So that's, let's see, BaSO4. So we find sulfate in the table. Sulfate's in the upper chart. So it's mostly soluble unless it's with strontium, barium, mercury, or lead. Oh, barium. It's with barium in this case. So it should be soluble, except it's an exception to being soluble, which means barium sulfate is insoluble. And then sodium phosphate. Phosphate's in the bottom chart. Insoluble unless it's with NH4 or group 1. Well, sodium is a group 1. And so an exception to being insoluble is that it's soluble. Okay, so this chart is nice. It allows us to predict solubility of pretty much any ionic substance. However, it can get time consuming. So there is kind of a need to know piece of information that will help us alleviate using this chart. And this is the 4 ions that will always make a compound soluble. Okay, this is really important. This is one of those need to know pieces of information. So there are 4 ions who are always soluble. There's never an exception. And so if you know that, we can kind of avoid using this chart sometimes because we can kind of cheat and use these rules of 4. So the first one is all group 1 ions. Okay, those are your alkali metals, your lithium, your sodium, your potassium, like we said before. So if you see a group 1 with anything, it's soluble. There's no questions asked. The second one is the nitrate ion. So NO3 minus 1. So again, if you see anything hooked to nitrate, that substance will be soluble. The third one is the ammonium ion, and that's that NH4 that we kept reading about in the chart. Okay, so if you see ammonium bonded with anything, it's going to be soluble. And the fourth one is the acetate ion. That's the one that can be written 2 ways, CH3COO. -1 or C2H3O2. Just two ways to write it. Okay, so what's nice about this is now if I gave you this and asked you to determine the solubility of magnesium nitrate, you should say, oh, nitrate. Nitrates are always soluble. And I did that in 1 second rather than having to go up here to the table to prove the fact that this substance is going to be soluble. Okay, so this is a really important thing to know, and it will help you save some time learning or figuring out solubility. Okay, and this is something that's expected. Students are expected to know about solubility. Okay, so then how does this finally work together with precipitation reactions and with double replacement reactions? So what we're going to do is a couple examples where we attempt to identify if a reaction produces a precipitate or not. So this is my example, and we're going to see what happens. So it says solutions of calcium chloride and sodium carbonate are mixed. Now, so those are my reactants. So I need to write my formulas, and then I'm going to have to predict my products. I didn't tell you the products this time, and that's where we're moving toward is, first learning reactions and then learning how to predict who our products are going to be. So let's see, calcium chloride. So calcium is +2, chlorine's -1, so CaCl2. And they told me it was a solution, which means it's aqueous. And my second reactant is sodium +1, and carbonate is CO3 -2. So Na2CO3, also aqueous because it's a solution. Now, we know this is going to be a double replacement reaction, 1, because it told us, but 2, because I have both of my compounds with the 2 pieces to the puzzle. I have a cation, anion, cation, anion. And so in a double replacement, I find the easiest thing to do is to switch the first 2 ions. So that now means calcium's going to be with carbonate, but we must look at their charges. Calcium's +2 and carbonate's -2. So CaCO3. And then now sodium is with chlorine. Be careful, don't do this. Okay, that's what students always want to do because they see the 2. But I have to go back to charges. I have +1 and I have -1. So there is no need for this 2 and this 2. Okay, we'll take care of that when we balance the reaction in just a second. So when you're writing these formulas, please keep in mind that I have to always go back and think about their charges. Okay, so let me get rid of this arrow. So now I want to balance. Okay, and this is where you can take care of the fact that on this side I have 2 chlorines and 2 sodiums, and over here I only have 1 of each. And I can fix that very easily by putting a 2 right there. Everything else is already balanced. Okay, so the last piece of this puzzle is figuring out what is the state of matter of my 2 products. And so this one's a no-brainer. It's sodium chloride. It's aqueous. This one, however, I need to consult my table for, because unlike before, none of these things fall into my 4 easy ones to know. So calcium carbonate, here's carbonate, insoluble unless it's with NH4 or group 1. Not the case. So this is going to be insoluble. It's going to be a solid. And so this is defined as the precipitate. Okay, that's solid. That formed from the 2 aqueous reactants. Okay, this is the precipitate. Okay, so that is a double replacement reaction. It's also referred to as a precipitation reaction because it produced a precipitate. Let's do one more, and that it will be, how about, I'm just going to give you the formulas this time. So let's say we mix silver nitrate and sodium chloride. Okay, so it's a double replacement reaction. Switch my first 2. Remember, you can only ever put a positive with a negative, and the positive thing always comes first. So I have now sodium with nitrate. That's a +1 -1 situation. So NaNO3. And then I have silver with chlorine. That's a +1- situation. So this one was easy. Now, I often get students asking, can I have written this instead? Right? Absolutely. You could have written this thing first and this thing second. And this is the same thing as, 3 + 2 or 2 + 3. It's the same thing. So it just depends on what you have written. In terms of balancing, everything's balanced already in this, so the coefficients are all ones. And again, let's identify the state of matter of my product. So this thing is definitely aqueous. Not only is it a group 1 sodium, but it's also a nitrate. It's absolutely soluble. Silver chloride, I have to check the chart. So chlorine, mostly soluble, but it has an exception of if it's with silver. And so in this case, this is going to be the solid, and this is the precipitate. Okay, and that's a discussion of how we identify a precipitate in a reaction. Now, not all reactions produce precipitates, and we'll get into that later, but some of them do, and that is how we go about figuring out who is a precipitate. There's only one more thing I want to add, and that is that precipitates can be white in color, which we've seen in class, or they can be colored. Okay, green, pink, blue, yellow. And this is kind of a big deal. If a precipitate is colored, then it contains a transition metal. Okay, and the transition metals are the metals from the middle of your table. And so, for example, if I see a blue precipitate, okay, I should now know that it contains a transition metal. Okay, all colored precipitates have a transition metal. So let's write that. I guess I kind of did right here. If a precipitate is colored, it contains a transition metal. However, not all transition metals produce colored precipitates. So this is one of those weird statements where you can say it one way, but the other way it's not always true. Okay, so that's kind of interesting. So like I said, if we see a precipitate that's pink, okay, it has a transition metal, no doubt. However, if we see a transition metal in a formula, it doesn't necessarily mean that the precipitate will be colored. A great example is what we just saw, which was silver chloride. Okay, silver is a transition metal, but silver chloride is white in color. So that's the perfect example to say that if a precipitate is colored, it contains a transition metal. However, not all transition metals produce colored precipitates. So that's something to keep in mind. We'll talk later about what colors belong to which metals. But this is an interesting piece of information that helps us when we see colored precipitates, we know they contain a transition metal.